Chevrolet CERV I 1964. CERV I, Chevrolet Engineering Research Vehicle, was developed as a research tool for that company's continuous efforts to understand automotive ride and handling phenomena under the most realistic conditions. The car was built at the Chevrolet Engineering Center at Warren, Michigan. The primary function of the CERV I was to provide Chevrolet engineers with a test platform from which direct visual studies were made from all types of ride and handling behavior under amplified conditions. The stated function of the CERV I largely determines its concept and final configuration. In order to realistically amplify vehicle responses to handling and road stimuli, the performance capability of the vehicle must be extended far beyond that of regular passenger cars. In other words, a high power-to-weight ratio is mandatory. By such means, suspension phenomena that are extremely subtle, and thus difficult to isolate within the performance capabilities of a regular passenger car, may be studied and treated quantitatively with the CERV I. Another fundamental factor in the experimental car's design is the visibility afforded by the body design. The streamlined, abbreviated body encloses the engine, transaxle, engine cooling system, and provide an open cockpit for the driver, from which all four wheels, in contact with the ground, are clearly visible. Some broad features of the CERV I are extremely lightweight to afford a horsepower-to-weight ratio such as that usually associated with high-performance aircraft, rear-mounted engine in unit with a fully synchronized 4-speed transaxle, the only passenger, the driver, sits well forward on the centerline of the car for virtually optimum visibility, and all four wheels are independently suspended to provide a high order of stability and positive handling. The wheelbase is 96 inches, 2,438 millimeters, and the car weighs approximately 1,600 pounds, 726 kilograms, ready to run. The chassis is an extremely stiff frame of chrome molybdenum steel tubes welded into a truss-like structure weighing approximately 125 pounds, 57 kilograms. The lightweight body, approximately 80 pounds, 36 kilograms, is aerodynamically styled and fully encloses the underside of the car. The body is fabricated of a glass fiber reinforced plastic somewhat thinner than that used in the Corvette body. The wheels are completely exposed to permit visual observation of tire-to-road contact during handling studies. Power for the CERV I is supplied by a specially developed, lightweight version of the Chevrolet 283 cubic inch V8 that develops 350 horsepower, 261 kilowatts, and weighs only 350 pounds, 159 kilograms. Such specific output, only 1 pound per horsepower, is rarely achieved in reciprocating engines, even in the most highly developed aircraft types. The dramatic reduction of weight was gained by using aluminum for the cylinder block, cylinder heads, water pump, starter motor body, flywheel, and clutch pressure plate. In the cylinder block, no bore liners are used and the pistons run directly on specially treated aluminum bores. Magnesium is used for the clutch housing, fuel injection manifold, and manifold adapter plate. Weight savings achieved through the use of lighter metals in the engine and clutch is in excess of 175 pounds, 79 kilograms. A number of special design features help the engine to develop 350 horsepower, 261 kilowatts. A special fuel injection unit has ram tubes of larger cross-section and 2,510 longer than those of the regular production design. Individual exhaust pipes of a tune length empty into large collector pipes and no mufflers are used. No cooling fan is required or used, and the water pump speed is reduced 30% by the use of a smaller crankshaft pulley. A small, 5-ampere generator is used in conjunction with a lightweight aircraft-type battery. In addition to the aluminum water pump mentioned previously, the engine cooling system consists of an aluminum radiator mounted forward of the driver, and 2 oil cooler radiators mounted one on each side of the main radiator. Power from the engine is transmitted in a conventional manner through the lightweight flywheel, clutch, and Corvette-type 4-speed transmission. Attaching directly to the rear end of the transmission case is the differential and final drive gear mechanism. A feature of the final drive gears is the ability to quickly change ratios so that vehicle performance can be as quickly tailored to a new environment. Power transmission to the wheels is completed through individual axle shafts with universal joints on each end, or a total of 4 in all. In 1972, Hot Rod magazine tested a prototype Chevrolet Vega featuring the all-aluminum V8. The fitted engine was the last of several 283 cubic inches, 4.6 liters, units used in the CERV I Corvette research and development in the late 1950s, bored out to 302 cubic inches, 4.9 liters, for the Vega application. Hot Rod's road test of the prototype with turbo-hydromatic, stock Vega differential, and street tires yielded quarter-mile, 400 meters, times under 14 seconds. The interesting rear suspension permits independent action of each wheel. Vertical movements of the wheels are controlled by 2 links, in which the upper link doubles as the axle shaft, and a rod, rubber bushed on each end as the lower. A third link runs from each rear wheel hub forward to the frame to transmit driving and braking thrust. Variable rate coil springs unitized with direct, double-acting shock absorbers are diagonally mounted at each rear wheel. Adjustment provisions in the rear suspension linkage permit variations in camber and toe-in to facilitate engineering studies. Front suspension is independent with high roll center geometry, and also utilizes unitized variable rate coil springs and shock absorbers as in the rear suspension. An 11/16 stabilizer bar interconnects the front wheels. The independent rear suspension design became the basis of the 1963 Corvette Stingray suspension. So that weight distribution during tests shall vary little if any. 2 fuel cells of rubber construction and total capacity of 20 gallons, are located on either side of the CERV I at approximately the fore and aft location of the center of gravity. Thus, the amount of fuel in the tanks at any given moment will have virtually no effect on weight distribution. Brakes on the CERV I are similar to the AHD type available on the Chevrolet Corvette. Cindered iron linings are used with fin-cooled drums, and the brake drum webs are lightened by drilled lightning holes which also permit the flow of cooling air. The brake drums are cast aluminum with cast-in iron braking surfaces. The rear brakes are end-board mounted next to the differential so that braking torque is transmitted directly to the frame without influencing any of the rear wheel articulating members. Braking effort distribution is 57% front and 43% rear to take advantage of the superior braking characteristics of the weight distribution afforded by the rear engine type vehicle. The brakes may be actuated by either one of 2 pedals so that the driver may use either foot depending on the particular driving situation. An unusual brake master cylinder utilizes 2 pistons operating in series so that at either the front or rear brakes fail, the remaining brakes can be actuated. The steering system features a high-efficiency recirculating ball-type steering gear of 12:1 ratio. Steering linkage is forward-mounted and is of a balanced relay link type. The overall steering ratio is a very fast 13.5:1 and only 2 1/4 turns of the steering wheel are required from lock to lock. Wheels are of cast magnesium alloy with knockoff hubs to facilitate quick changing. Wheels of 15 inches, 16 inches, 17 inches and 18 inches diameters with rim width of 5, 6 inches, and 8 inches are used. The car is currently on display in Detroit, Michigan at the Renaissance Center on Level A within the GM World Display Space.